In this three-part video, we will be understanding one of the most important innovations in deep learning in the last few years, attention. Attention started out in computer vision as an attempt to mimic human perception. This is a quote from a paper on visual attention from 2014. It says that one important property of human perception is that one does not tend to process a whole scene in its entirety at once. Instead, humans focus attention selectively on parts of the visual space to acquire information when and where it is needed, and combine information from different fixations over time to build up an internal representation of the scene, guiding future eye movements and decision making. What that means is that when we look at a scene in our daily lives, our brains do not just process a visual snapshot all at once. Instead, we selectively focus on different parts of the image and then we sequentially collect and process that image over time. For instance, imagine you're given an image and asked to find the person wearing an orange t shirt. Instead of scanning the whole image, your eyes naturally focus on the center as the rest becomes irrelevant. This is an example of applying attention. The idea in computer vision was to develop the method that mimics this behavior in models. In machine learning, attention provides a way for models to selectively focus on important parts of the input, especially in tasks where processing happens sequentially. Attention is a concept that powers up some of the best performing models spanning both natural language processing and computer vision. These models include machine translation, image captioning, speech recognition, and text summarization, and many more. In machine translation, attention enables the model to focus on specific relevant parts of the input as it generates the output step by step. This is different from earlier models, which could only process the input once before producing the entire output. When attention was incorporated in sequence to sequence models, they became the state of the art in neural machine translation, which ultimately led Google to adopt attention mechanism for Google Translation at the end of 2016. Let us first touch on the applications before diving deeper into the concept. The term sequence to sequence RNN might sound abstract and doesn't quite capture the range of incredible tasks that this model can perform. Think of it this way. We have a model capable of generating any sequence of vectors which can represent letters, words, images, or anything else. As long as it can be represented as a vector, it can be used in a sequence to sequence model. The model learns to generate a sequence of vectors based on an input sequence. So, what can we do with this? For instance, if you trained a model on a dataset where the input is an English sentence and the target is a French sentence, you have now created an English to French translator. Train it on a dataset of news articles and their summaries, and it becomes a summarization tool. If you use question and answer pairs as the data, it turns into a question answering system. Train it on dialogue, and you have built a chatbot. And it doesn't stop just with text. Sequence to sequence models are also used in tasks like image captioning when combined with convolutional neural networks, and they can process audio sequences as well. The possibilities are vast once you understand the potential of sequence to sequence models. The key challenge is finding the right dataset and guiding the model through its learning journey. Let's take a closer look at how sequence to sequence models function. We'll start with a high level overview and then gradually dive deeper. On the left, we have the encoder, which is a recurrent neural network that reads the input sequence. It passes what it has understood to the decoder, another RNN on the right, which generates the output sequence. The information passed from the encoder to the decoder is a fixed type tensor known as the state or context. Regardless of how long or short the inputs or outputs are, the size of this context remains fixed, as defined when building the model. At this high level, the process involves the encoder processing the inputs, summarizing them into a context variable, and passing it to the decoder, which generates the output sequence. Going a level deeper, since both the encoder and decoder are RNNs, they operate with loops. enabling them to process sequences of inputs and outputs. For instance, if we are building a chatbot and ask, "How are you?" the input is tokenized into four tokens. The RNN processes each token over four time steps, transforming its hidden state at each step and passing it to the next time step. This process can be visualized by unrolling the RNN, representing each time step as a separate cell. Although in reality, it's the same cell reprocessing new inputs and updating the hidden state. Now, what is a hidden state? In simple terms, it consists of hidden units within the RNN cell. In practice, it's often the hidden state within an LSTM or long short term memory cell. The size of his hidden state is a hyperparameter that determines the model's learning capacity. A large hidden state allows the model to capture more patterns but makes it more resource intensive to train and deploy due to increased processing and memory demands. On the decoder side, a similar process occurs. The decoder begins with the state generated by the encoder and generates the output step by step. As with the encoder, the decoder can be unrolled to show that it feeds each generated element back into itself, which helps maintain coherence between time steps, as each output is informed by the previous one. So far, we understood that encoder processes the input, converting it into a single representation, often called the context vector. This vector captures the essential information from the input sequence and is then passed to the decoder, which generates the output sequence. In machine translation, both the encoder and the decoder are usually recurrent neural networks, often using LSTM cells. The context vector is a numerical representation of the information encoded by the input, and in real world models, it can be a 256 or 512 dimensions long or more. We'll visually represent this vector with a length of 4, where the brightness of each cell reflects the value of that hidden state. Let's revisit a simple example, but this time we'll look at the hidden states within the encoder. At the first time step, the RNN processes the first word and generates the first hidden state. At the second time step, it processes the second word and uses the previous hidden state to produce the next one. By the final step, the last hidden state becomes a context vector that gets passed to the decoder. However, this is where sequence to sequence models face limitations. The encoder can only send a single fixed size vector regardless of how long or short the input sequence is. While increasing the number of hidden inputs in the encoder could theoretically handle longer inputs, it causes overfitting with short sequences and performance issues as the model becomes more complex. This is the challenge that attention mechanisms address.